In this slide, we will move on to the bracketing methods which are mentioned in chapter 5, and the functions which change sign in the vicinity of a root are of interest especially, and we show these kind of roots in the graphical methods section. So to be able to identify a root when we change a sign for the bracketing methods, we use two initial guesses, and it should bracket the root actually. Which means one of the initial guess should be on the left side and one of them should be on the right side. So it should cover the roots in between these two guesses, let's say. And at each iterations, we will narrow down the brackets or the width of the two guesses, and eventually we will get the correct answer. The bracketing methods employ different strategies to reduce the width of the brackets, basically, and incremental search methods are these methods that we will talking about here. And these actually locate an interval where the function changes a sign. Basically, the interval is divided into a number of subintervals, and the location of the sign change, and consequently the root is identified more precisely. So because eventually we will make guesses, but if we don't know where the sign changes, that's not easy to bracket the root. That's why we need to divide the interval into subintervals, search for each interval if it is changing the sign or not. If there is one interval changing the sign, then we focus on that and have a narrowing down approach on that region only. Yeah, each of these subintervals is searched to locate the sign change, and the process is repeated and the root estimate refined by dividing the subintervals into finer increments. So there are two types we describe in this course in the chapter 5, the bisection method, which is widely used, and the false position method. Let's look at these in the following slides. First, let's look at the bisection method. So this is also called binary chopping, interval halving, and Bolzano's method as well. And the feature of this is that the interval, because we are bracketing the root now, the interval is always divided in half. And we have three simple steps. And first of all, because it is always divided in half, that's why it's called interval halving method as well. So if a function changes sign over an interval, the function value at the midpoint is evaluated. So if we find a sign change, then the midpoint, so we will halve to be able to halve the interval. We find the midpoint between the two bounds, then and calculate the function value for the midpoint. Then we find the location as the midpoint of the subinterval within which the sign change occurs. And we continue this process repeatedly to obtain a refined estimate. For example, here there is a 3 iterations. You can see, first of all, we have a bound of kind of between 12 and 16, and in between we have this value. So we have a sign change, and between the midpoint to the left or right, we decide which side changes the sign, and we see that the right side changes the sign. That's why midpoint becomes the lower bound and upper bound stays the same. Then we continue. So here again, between 16 and this value, then we narrow it down, so we actually get the half bound, and we check the sign again of the function. From here, the left side has a sign change. That's why we picked the right side as the midpoint. The left side becomes the same. This value is the same now. And in here also we refine again. We get the half point and check which part, for example here, and which part, left or right, getting the sign change. Wherever makes the sign change, we take that part into account and again halve the region. So we continue like this, refine the bounds and get the solution eventually. A simple algorithm is as follows. First of all, in step 1, we choose a lower XL and upper XU guesses for the root such that the function changes sign over the interval. So for this, we may need to use the graphical method to see where it changes the sign. And actually, if we don't have the graphical demonstration of the function, there is an easy way as well. We simply multiply the function values of xl and xu like this. And if it is smaller than 0, because one of them for sure should be minus and the other should be positive to be able to have this. And the sign change means that actually, if this is minus and this is positive, for example, or this is minus and this is positive, then it will be smaller than 0. If we make this change, we will understand that the two guesses, the function values, changes a sign. Then we made good guesses. Then we continue. What we do is we simply divide the summation of xl and xu by 2 to get the middle point. So the estimate will be the xr will be the middle point like this. Then we will make the following evaluations to determine which subinterval root lies. So we will check the left side and right side to see if there is a sign change. So for example, we will check the left side, lower bound, times the function value of this midpoint. If this is smaller than 0, because as we said earlier, if this is plus, this is minus, for example, then this side is good for us. Then the root will be on this left side or lower subinterval. That's why we actually need to set the upper bound to the new midpoint. Instead of using the initial upper bound, we will use the new upper bound now. But the lower bound will be the same because the root lies on that side. The other alternative is that the root, the multiplication of these can be positive, then that means these both are positive or both are negative. That means the root lies in the upper side because we multiplied with lower side and it was greater than 0, what was positive. That means the upper side becomes actually negative, or the upper bound has a sign change. That's why we set, instead of xu, we set xl, the lower bound, as the new midpoint, and xu stays the same. The third alternative, which is not likely actually, the multiplication of these will be 0. Then we actually find the exact root value if it is 0, because that means this is 0. If this is 0, we want the function to be 0 anyway. xr makes the function 0. Then we find xr and we terminate the computation. So we continue to this until we find this C alternative. If these are true, then we repeat this step. If this is true, we stop basically. And this is how we apply the bisection method. It's very simple and it guarantees how to find the root of an equation. So we will need a termination criteria for the bisection method because finding the root which gives exact 0 is not possible. So we can have a value near 0 but not exact 0. That's why we need to have a stopping criteria. So we can set a limit, a threshold value, epsilon s, near 0 maybe, we can say. And we want an error value smaller than that. For example, epsilon t, we already talked about this. This is if true value exists, we can use the true percentage error. And if you remember, it was epsilon t equivalent to true value, let's say x true, minus xr, the predicted value, divided by x true, times 100. And we want this to be smaller than epsilon s. And at each iteration, we change this value to the new value and calculate this and check if it is smaller than this. Whenever it gets smaller than this value, we stop and say that xr value is our result actually. But in real life, we usually don't have the true value. So using this usually not possible. That's why instead of this, we mentioned this earlier as well in previous slides, that we can use an approximate percent error. So what we do is simply with the new iteration and old iteration, we can calculate an error value because we know that in numerical method, we will eventually get smaller differences between the previous and current iterations. And here that's why calculate EA, epsilon A as and we will use XR, the predicted values, because we don't know the true value. XR new, let's say, or the current, minus XR old, or the previous, divided by XR new, times 100. So we want this to be smaller than epsilon S. And this is a pretty good termination criteria for us now. At each iteration, we calculate this error by comparing with the previous value. So we can also modify this error to get a modified error metric. And for that, what we do is simply, we first identify the difference XR new minus XR old. If you remember, we actually determine an upper and lower bounds, and the XR new minus XR old are actually known as XU minus XL divided by 2. The reason of this is that simply the XR new, we know that XR new is just the midpoint, so we can find that as XL, the lower bound, plus XU divided by 2. And so by using this, we can simply find a new error metric. Let's write this down into here, this one into here, and this one to the nominator, to the top, and let's write this again. So this new result is the new error metric, epsilon A, when we write these, is simply XU minus XL divided by, this is XL, XU plus XL times 100. And now we can have a stopping criteria which is actually like this, smaller than the predefined threshold. So we usually use this instead of using the XR values, because we already determine initially at the beginning XU and XL, then we change these based on the sign change by having a midpoint. And simply using this will be more convenient instead of using this. So this will allow us to calculate an error estimate based on our initial guesses as well, because these can be the initial guesses. And in our first iteration, we will be able to have an error estimate too. So that will, from the beginning, help us to determine what's going on. So you can see on the left-hand side a figure of previous and present iterations. In the previous iteration, actually the XOld is simply X new minus X old. And the X new is here, the X old is here, and the difference divided by 2 is simply this value. And we will use this as the stopping criterion in the bisection method. We can also have an error estimate for the bisection method beforehand. So also the number of iterations especially required to attain an absolute error can be computed a priori before starting the iterations. How can we do this? Let's start learning that. This can be seen by recognizing that before starting the technique, the absolute error is, let me write the absolute error before starting the iterations, simply absolute error EA in the first iteration, zeroth iteration, actually 0 is the initial iteration. So we determined an upper bound and also an lower bound, and at the 0th iteration, and this is just the initial error, let's say delta x, the initial absolute error. We can make this like that to be absolute. So the superscript zeros designates the iteration. This is the 0th iteration, And after the first iteration over here, the error becomes the half of this, because we are always halving the bracket. This is the bracket, the delta is the bracket, we are halving this. That's why at the first iteration, which means EA1, the first iteration, is equivalent to delta x0 divided by 2. We are halving it. And at each succeeding iteration, the following iterations, we are always halving the error. And that's why we can have a general formula relating the error and the number of iterations n. So simply, we will have always this and divide it by 2 always. And that's why the bottom part, or the denominator, will have 2 to the power n. And for nth iteration, EA nth iteration, will be delta x0 divided by 2 to the power n. This is basically determine the error value for us. And if we have a desired error value determined before, this equation can be solved for, let me write here, n is equivalent to the logarithm of delta x0 divided by e ad, and this is divided by logarithm 2. And simply, if we write this again, it is, let me write it here, n equals, if we simplify this, because it has log in numerator and denominator, it's log 2 delta x0 divided by EAD. This gives us, and so we basically isolated this n here, because this is a mathematical equation, and obtained this value. So this is an important function or formulation to find the number of iterations. Simply, we determine an initial error value smaller, even enough to get 0. I mean, this can be near 0. And we will have the first difference. So these are the initial guesses. That's why we can have this. And a predefined value, divide these, get the logarithm, and we find the number of iterations. In this slide, we will make a comparison of the approximation error and true error for the bisection method. And in a general rule of thumb, the approximation error is always greater than the true error for the bisection method. And we actually showed this for the prediction of the parachutist example. For other numerical approximations as well, the true error was smaller than the approximation error, but it can change in some applications. But for bisection, it is always like this. This always is important here. Always the true error is smaller than the approximation error. And let's try to show how this works. So for the bisection, we have a midpoint calculation to be able to get the new prediction. It's basically lower and upper bound summation divided by 2. It is the midpoint. And the true root is within an interval of delta x divided by 2. So here's an example plot. You can see at A that the xl and xu, so the middle point is xr. The true root is here. So delta x divided by 2, delta x divided by 2 are the range of the new value and the bracket limits, let's say. And in A, the true value lies at the center of the interval here. So in B and C, on the other hand, what we do is, so we selected this, then we compare this, we take this as xu and xl, between xl and xu, we will have the midpoint again. Or in C, with this being xl, the lower bound, between the upper and lower bound, we will have a midpoint for the new value. And the true value lies near the extremes, actually. So it can be either the extremes, so from midpoint to the right extreme, or from midpoint to the left extreme, or in between. So the extremes are always delta x over 2. And the true value minus midpoint, that's why is always smaller or equivalent to half of the interval length, delta x over 2. So it's always between this or this when we halve it always. And that's why you can notice on this left hand side that the discrepancy between the true value and midpoint of the interval never exceeds half the interval length, delta x2, like as we explained here. And on the right hand side, because we know that delta x divided by 2 is x new minus x old, let's see the figure below, the previous iteration, so lower bound and upper bound, we got the midpoint as the x are new, but this is actually for the previous iteration. So we set this now as the lower bound of the present iteration. This is the lower bound, upper bound stays the same, and now we can again halve the range and we get the x new value. So this is x old, this is x new. The difference between this is like this distance, which is smaller than the delta x distance actually, or this is always delta x divided by 2. And that's why the approximated error, so this is approximated, the previous approximation and new approximation, and difference of this is delta x divided by 2. It's always an exact upper bound on the true error, because the upper bound of the true error we showed here is delta x divided by 2 as well. And for this bound to be exceeded, or if we want to exceed this bound, the true root would have to fall outside the bracketing interval. So we know that now here, for example, the true root is between here. In the next iteration, we know that the true root is between here. And now here, it will be between here, for example. That's why the true root is always between these, between the x old and x new values. It cannot exceed this, so it cannot be here. That's why it's always between this delta x divided by 2 value. So the falling outside of the true root cannot occur for the bisection method by definition. And this is a big advantage, because it makes the approximation error to be getting smaller each time, so that we can always find a true root. Let's say we will always find it with the bisection method. Bisection method is very slow, actually slower than the other methods that we will show later on, but it guarantees finding the true root. So this is the neatness or the advantage of this numerical method for the bisection method. Actually, it's very attractive and widely used in the engineering applications as well, for this reason of guaranteeing finding the actual root.